F.3, merge operation. In this part, we really need to solve our problem number 16. Merge two ordered arrays. All right, so we did some analysis in the previous video. So now let's look at the implementation. So we try to get there. Yeah. All right, so when we start, we want to look at this question: how to achieve balanced subarrays. How do we split our original array to get balanced subarrays? Here we need to use the intuition. Very simple. Just use our imagination, intuition, so we can do it easily. Yeah. All right, so the idea: whenever we merge two subarrays, make them of equal size, we try to make our data, arrange the data into subarrays so that we just merge two subarrays of equal size. In that way, we can avoid very poor worst case. And hopefully, when we use this way, we can achieve that big theta. Remember, so let me recall another time, big theta n log n efficiency. That's our goal. Okay. All right. Yeah. So let's use our intuition to do the split. Yeah. All right. So given an array, this whole line segment representing given array. Yeah. The first time when we split, okay, so we make the split as even as possible. Yeah. So we cannot guarantee the two subarrays have equal size because it depends on the number of elements in this array. You can have even number and odd number, right? Yeah. So there are two cases: even number of elements and odd number of elements. For the even number of elements, you can get even split, right? But for the odd, not even, but close to even. So one subarray has one more element than the other one. That's okay. So that kind of thing is good enough for the split. Yeah. So let's do it. Yeah. All right. Yeah. So we call almost even. Yeah. All right. So we find a point in the middle and split it to subarrays with almost equal size. Yeah. All right. Second round, for these two subarrays, we split them also in the middle and get this time 4 subarrays with almost the same sizes. Yeah. And so on. Next round, split like this. Okay? Yeah. On and on. Yeah. But you have to stop somewhere, right? You cannot split in this way forever. So you have to stop somewhere. So stop splitting when each file contains one element. One element, you cannot split furthermore. Yeah. So you have to stop if you get a one element array. After that, then we can do the merging. Yeah. Merge two adjacent subarrays. Yeah. One element array we treat as sorted, right? Well, special case, already sorted. We just merge two adjacent one element arrays. That's easy. One comparison, we can get it sorted. Yeah. All right, so we do the merge, the first round, like this. All right, yeah. Next round, to an adjacent ordered array. The details at this point we can skip. How do we merge? That question we haven't answered. Yeah. Starting from next slide, we will work on it. Yeah. So here we don't need to worry about it. Yeah. All right. So here you can see merge the result subarrays. Yeah. After the merging, each one is ordered. Yeah. So in this way, every time we merge two adjacent subarrays, at the end, we get the whole array sorted. That is the new idea. This is the idea for our new sorting algorithm. Think about it. It's quite different from all our old sorting algorithms. It's a completely new sorting algorithm. Okay? All right. So after we get that, we hope it can avoid poor case performance. So that is the reason we need to develop this new sorting algorithm. Okay? Yeah. But after we get the whole problem solved, then we need to do performance analysis, efficiency analysis. Yeah. We will do that later. Yeah. First, we need to solve the problem first. Okay, all right. Here you can see the main step here is the merge step. Merge two adjacent ordered arrays. The merge step, we need to get the details of this step. Details. Yeah. From the next slide. So I will draw diagrams to show the details. Yeah. All right, so let's start. Yeah. All right, let's work. Yeah. Two arrays. We assume they already sorted. Now, how do we merge these two arrays? With the number of comparisons as small as possible. Yeah. All right. To merge these two, so we start from the smallest element of each array. Yeah. A0, the smallest of the first array, B0, smallest of the second array. So we compare them. Okay? So when we compare these two elements, there is a minimum and a maximum. So minimum, yeah, because A0 could be the minimum or B0 could be the minimum. So we don't know which one. Yeah, whatever it is, we just take the minimum. Then the remaining one, the maximum one. Yeah, the minimum one. So look at this minimum one. Minimum one, the minimum element of A0 and B0 will be the minimum of the whole array. Minimum of the whole array. Because A0, the smallest of the first array, B0, smallest of the second array, the smaller one of A0, B0 must be the smallest of all the elements. Yeah. So you can see that one, we just use one comparison, we can make the minimum main zero in place. Yeah. So we will use that phrase another time, in place. So this minimum zero in place. Okay, all right. Then the max zero remains. Yeah, so here max zero could be B0, could be A0. Here we just use the B0 as the case one. Yeah. A0 similar, so we do not need to repeat it. Yeah, it's enough to look at one representative case, right? Yeah, here, max 0 equals B0. next one, we need to compare B0 with A1. We want to see which one is smaller. Okay, this time we use min1, minimum sub 1 for the new minimum. Okay, the new minimum, yeah, of A1 and B0. Yeah. So the min1 should go to the second element in the result array. So this time, second one is in place. Here you can see every time when we do just one comparison, we put one element in place. How good it is. Yeah, pretty good. Yeah. All right. Then we can keep doing this. Yeah. All right. Then this time we want to look at the worst case of this step. Because when we keep doing, eventually we'll put all the elements in place, right? All the elements in place, right? Yeah. So, all right. You can see in this step, every time when we get a new min in place, yeah, we need just one comparison. But the last one, we don't need to do the comparison, right? If already the last one, right? Yeah, whatever the max is, you directly put it at the end of this result array. No comparison needed. Yeah. So that means you can save one comparison. All right, yeah. All right. So yeah, so you have this. Yeah. So you can see now the number of comparisons for the worst case. You can get an answer. Yeah. So think about this. The number of comparisons for the worst case. The maximum number of comparisons you need to merge these two arrays. Okay, so that means other than the last one we don't need any comparison, right? Each one we need one comparison. Okay, each one we need. That's the worst case. That's the worst case. Yeah. Because we may have some other cases better than this. Yeah, we may have cases better than that. Yeah. For example, if, so we do comparison in this way, so interchangeably, so one from the first one, one from second one, compare the smaller one, put in place. Yeah, we do this interchangeably, right? Yeah, all right. Then think about there is a special situation. There is a B element. Let me call BI, okay? BI element somewhere in the middle of the B array. This BI, when I do comparisons, I find it beats all the elements in the A array. Already beats all the elements in array. Okay? Yeah. All right, so the BI, all right? Yeah. When you do comparisons, all A array, so we put here, okay? Yeah. So then BI here, okay? After that, the B elements after BI, we don't need to do comparison. We can put directly back in the, in the result array. No comparisons. We can put the remaining all array. We just copy. Okay. Those cases are not the worst case. The worst case is, so you're not as lucky as that. You're not as lucky as that. So you need to keep, keep doing. You don't have some element in the middle that can be all elements in the other array. Yeah. You need to do comparison until the next to the last one. That's the worst case. All right. Yeah. Try to imagine those cases. Okay. All right. If you understand that, Now the answer for the worst case. The number of total elements minus 1. The last one, you don't need to do comparison. But before the last one, you need to do one comparison for one element in place. All right, answer is 2k minus 1. 2k minus 1. Okay, all right. Then we want to generalize to this worst case to more general merge step. That's a special step. Two arrays are equal, evenly distributed. But in the real world problem solving, sometimes we may need to merge two arrays with different sizes. That's possible, right? So I want to still look at that question. If we merge two arrays, ordered arrays with different sizes, what is the worst case? Right? Yeah. Just a little more extension, we can get that. Yeah. All right. So we still do the similar things. Yeah. Our analysis all true, but for the last step, we don't need to do last element. We don't need to do any comparison, right? Yeah, no comparison. But so you can see the answer. If the first array has size n, second array has size n, then the total number of comparisons, n plus n minus 1. The total number of elements, minus 1. That's the answer. Similar analysis as the previous slide. Okay. All right. Yeah. Then the best case. I also want to take a look at the best case for the general merge step. Yeah. So for the best case, now we try to use our previous analysis. Okay. But we push to the other end, right? So not this end, to the opposite end. So using your imagination to get the best case. Yeah. All right. So this time, what is the strategy? The strategy is you try to imagine using your intuition to do some imagination. The strategy is try to exhaust one of the two arrays as early as possible. Try to exhaust. So if you can exhaust one of the array, two arrays, one of the two. Yeah. Exhaust, what do you mean? So one element in one array beats all the elements in the other one. Or the smallest element in one array beats all the elements in the other array. Or the other way around, one smallest element in the first array beats all the elements of the other array. Okay? Yeah. Two possible cases. Which one is better? That's the better one corresponds to the best case. Okay? Yeah. All right. The better one, we exhaust the shorter array. Because when you exhaust the shorter array, you use fewer number of comparisons. After that, remaining elements, you just make copy. No comparison. Just make copy directly. So that will be faster. Yeah. All right. All right. So now we need to answer the best case efficiency. Our final answer. Easy. The minimum of m and n. Minimum of m and n. That's the best case. All right. So that's it. Yeah. That's the merge step. Merge operation. Merging two ordered arrays to get a new ordered array. The best case, the worst case. Okay? So after you understand this step, next we are ready to solve the sorting problem. Okay, so finally we need to solve the sorting problem. Yeah. But we will do it in our next part. Yeah. So this part, this class, 3 videos, we completed. Okay, yeah, so we stop here, and part G, A, B, C, D, E, F, G, part G, so we will complete the remaining merge sort part. And do analysis. Remember, we need to do analysis. We need to get the worst case. N log n in part G. Yeah. All right, so that's it.